Hello, and welcome to our fifth session. As usual, let me share my screen. Wait for it to go a bit weird. And it should be up now. So if you cannot see it, maybe we'll give it 1 second. If anyone was here before, they know that there was one session that it didn't go. So I just want to make really sure that it's working. All right, just to test if it's working and the chat function is on, please could you let me know what course you are studying? Is it AI, SL, HL, or AA, SL, or HL? I'm also going to share the Notion page just in case anyone doesn't have it. And that will have all of our upcoming sessions and links to past videos. So I'm sharing that. So there you have all the information. And I'm just looking over here because I have my iPad with the chat. So I'm just looking there to see. All right, good to know. So just a note that if you are AISL, this is not going to be in your course. So I'm sorry if you are in AISL, if we have anyone of that here, but this is not for AISL, but for all the others. So there's a few differences in the different courses, but I've tried to keep it very much something that's overlapping between the AA and the AIHL. Great, so I see, yeah, everyone is AA. Perfect. All right, then let's get started. So I'd like to start with a warm-up question. What are the special angles? So just the ones that we need to memorize if it's a paper 1 paper where there's no calculator allowed. What should we memorize, or at least know how to calculate using special triangles, or there's like hand methods that you can use. You can look those up. Some people prefer the visual hand method. Or there's the table method. There's a few different ways that you can remember these. So please put in what you know. And if you're not sure, I'll show you my method. I like the triangles. I think they're the easiest to remember. But if you want to look at different methods, just search up how to remember special angles, and there'll be a million different ways you can do it. Yes, thank you. 30, 45, 60, and 90. Awesome. So just in case you don't remember, I'll show you how I do it with the triangles. We have our special triangles. Excuse my ugly triangles. They're all 90 degrees. There are 2 of them, one for 30 and 60. So we have 60 degrees, 30 degrees. These are not to scale. And we have them looking like that. You can always just remember 2 of them and use Pythagoras to find a missing one, but I think it's good just to remember all of them as they are. 45 degrees, sides of 1, and root 2. So these are good to memorize, all those other methods I mentioned. And from here, you can find out sine, cos, and tan of 30, 60, and 45 just with these triangles without a calculator. And this will come up. So it is extremely important that you do remember that. So for example, let's do, we want to know, for example, sine of 30 without a calculator. So the exam question leads you to something where you need to know sine of 30. So sine of 30 is opposite, well, sine is opposite over hypotenuse. So here we have opposite being 1. And hypotenuse being 2. So there we go. Sine of 30 is a half. And that's how you can find all of these angles. All right. So just a little bit of a recap before we get into some examples and exam questions. So we know by now that sine and cos and tan are going on forever and ever and ever in both directions. So there are many solutions to questions. For example, sine theta equals 0.5 is saying, where does the sine graph, this curve over here, when is it equal to 0.5, which is this line going across like that? We can think of it as y being the graph of sine theta and y being the graph of 0.5. So what they're actually asking when they say, when is sine theta equal to 0.5? They're saying, well, when is the graph of sine theta equal to the line y equals 0.5? And we're finding their intersection points. These are all just intersections between the lines. So you can see there are infinite solutions. And obviously we don't have time for that in our papers, and we are going to do a lot of it by hand, so that would take too much time. So they'll give us a restricted domain. So they'll say, find all the values between 0 and 2 pi, for example, for in radians, or between minus 90 degrees and 270 degrees. The question could be like that. And it's very important. My biggest tip for you is when you're answering questions with this, that you highlight. You can take a highlighter into your exam. Highlight these things. That goes for any question where they give those little pieces of information, like the answer can only be all positive numbers, and you get 2 solutions, one's negative, one's positive. It's so easy to be caught up in the question, and you get the answer. You get x equals such and such, and then you forget to look at the domain. And that is always going to be worth an extra mark, noticing that you have to discount one of the solutions. So I recommend you highlight that domain or that restriction or any kind of extra information that they give, just so when you're at the end, you see, oh, I've highlighted, I need to go back and just double check that my answers still match what it says. All right, so to start with, very important. When you do on your calculator, let's say you're trying to find an angle. So you have x equals sine minus 1 of, I don't know, 15 over 20. Let's say you get something like that. Your calculator, when you put it in, is going to only give you one value, just one answer for this, because it's only programmed to give you what we call the principal value. So it's not going to give you those infinite solutions. It doesn't know how to do that. So you are going to get the principal value, and from there, you're going to use different methods to figure out what the rest of the solutions could be within your domain. So this is something that's quite commonly known, that if you have sine x equaling to, let's say like in the previous one, 0.5, you could get one solution that's your A or alpha, your principal value, and then to get your next value, you do pi minus that principal value, or the same for cos. Now, this is something that a lot of people use. I'm not going to use this. I find that the method that I'm going to show you, students tend to remember more. This ends up being forgotten or confused. There's just quite a few things that can go wrong with this that I see as an examiner as well in question papers, that these get switched around. People don't really understand them. They're just applying a formula. So I'm going to show you a method that I like to use that I think it works for every time. And it's kind of one method that you can use. And it's just going to work every single time. And you don't really have to remember anything. But if you do like to use this, by all means, when I'm going through the questions, feel free to use that, or whatever method you have. Some people graph them. Some people do the like a sine curve on, and they calculate from that. There's many different ways you can do it. So none of them are wrong. And obviously we don't have all the time to go through all the methods. So I'm just going to do the one that I think works the best. So yeah, let's see how that looks like. So that method is using cast. So don't know if you've heard of cast. Anyone heard of cast? This is just taking out quadrants and saying where all of our values are positive. Just saw a comment. Yes, for AISL, this is not relevant for you. So I apologize for that. Hello. So this will not be in the AISL course. All of this is for AASL, HL, and AIHL. So apologies. But we will have 2 sessions tomorrow and 2 sessions in the week that will be for AISL. So, but you're welcome to stay anyway, maybe pick something up. All right, so we have cost. This is going to tell us where our angles are positive or negative and which ones to use. So our method begins with this. So cost means that in A stands for, oh, no, didn't want that one. Cos stands for all are positive. So sine, cos, and tan, all are positive. And if you've never seen this before, don't worry, it will make sense when I show you an example. For here, it's saying that sine is positive. Here, tan is positive, and cos is positive. So we remember cost, and very important to remember, it doesn't go in the way that you think it might, like how we label quadrants, but C starting down here. So you can just remember in our first one over here that we work with, this is where we get our principal angles, all are positive, and then from there it's cost. And that means if sine is positive, then cos is negative here, tan is negative here, and likewise negative, negative, etc. I'll just write that anyway. And sine negative. All right, so all you need to remember, though, is just that the ones that they stand for are positive, which means then the other ones are negative. Okay, so that's going to be a helpful step for us in working out when we're solving these equations and working out like on the unit circle where we're getting positive or negative and which solutions. Then just to quickly go through radians and degrees, a quick little recap. A lot of people struggle to remember how to convert between them. I think the easiest way is to start with writing 360 degrees and 2 pi on the top. You can do this at the beginning of your exam, just write it on the front page. So you don't have to keep calculating every time and risking making a mistake. So do this once, keep it on a spare piece of paper, and then you can always have that to refer to. So it's like a little cheat sheet. You can write it on your formula booklet. I think that makes sense. So you start with, you just have to remember that 360 is 2 pi. And then if we want to go down, like half of that, 180 degrees, is just half of 2 pi, which is pi. Half of that again, 90 degrees. Half of pi is just pi over 2. Half of that again, we'll leave a little space there. Half of that, half of 90 is 45, so half of that is pi over 4. And there we have some of our most important angles. Then we also have 60 degrees comes up, that's important. Well, if you think about going from, let's say, 180 to 60 degrees, we divide by 3. So we also, to go from pi to 60 degrees, we divide by 3. So that's pi over 3. And same for 30. If we go from 180 degrees to 30, we're dividing by 6. So to go from here to there, we're dividing by 6 again, which is pi over 6. So that's how we can get those just set up. Those are all the ones we're going to need to remember. And 270, sorry, I didn't put that in order. It's a good one to remember, 3 pi over 2. So these are the important ones that we should be remembering. And if you just start with these two at the top, then you can get all of the others without having to memorize or making a mistake. If you're in HL, you probably have worked with these so much that it comes to you a bit more naturally. Okay, so with that, we can begin. So as we said, solving graphically, I just want to show you how to do that on your calculator. So if you have a paper 2 question, then you should definitely solve the equations like this. You don't get any more or less marks, but you save a lot of time and accuracy. If it's a paper 2, you have your calculator, solve it graphically. So remember what we're saying is that sine x is the graph of y equals sine x. And this is the graph of y equals 0.5. Then they give you your domain, so highlight your domain, so you remember to check that. That's going to be useful for the calculator. And we're going to plot these on a graph. We're going to give it the domain, and it's going to give us our solutions for us. So let's take a look at how we would do that. The rest of these, mostly I'm going to do by hand, just so you know. Okay, so we have typing it in. I'm using a TI Inspire. If you have TI-84 or Casio, it'll be something similar with your graphing. And if you have any troubles, you can message me on up here. my Instagram page, Miss IB Maths, just at Miss IB Maths. If you have any questions, because I know some people are not working with TI Inspire, just send me a message and I can tell you how to do it. And ChatGPT as well is a good one for telling you what to do. Okay, so we want sine x. Remember to put this in brackets, otherwise it doesn't recognize it. See, if we just do like this, no graph, it doesn't know what to do. So we have to do brackets around our variable, and we will fix that. That will be the scale, and we want I need to remove that one. It's messed up everything. I'm just going to start with a new graphing page because it's messed it up. If anything weird happens, just start again. So sine x. Then next one, 0.5. And let's change our window. All right, so we wanted between 0 and 2 pi. 2, and where's my pi? And then my sine graph only goes between 1 and -1. So I'm going to say -3 and 3, just so I can see what's happening with it. Okay, and why are we doing this? That is not what it's meant to look like. Let me just fix that. No, what menu? There we go. So let me just change my domain again. Sorry, I'm having a bit of a delay on my clicking, so it's going a little bit ahead. Okay, so I want Windows settings, and I want it from 0 until 2 pi. That's what my domain was. -4 and 4, that's fine. Okay, never mind. This is sometimes does this. Let's just go trig. Okay, there we go. So what we wanted is between, it's because I'm in degrees, that's why. That is why. This is also a great thing to remember. It's amazing how many times you get stuck with this, even me, which is a very silly mistake. There we go, finally. Okay, that was the key. I'm working in radians and my calculator was in degrees. So now we can see it. It is on our domain between 0 and 2 pi, which is 6.28. So don't be worried about that 6.28. That is just 2 times pi. All right, so this is the part of the graph they want us to look at, and they want us to know where are those solutions. So we have over here, there's an intersection between 0.5 in our graph and here. So we know that there are going to be 2 solutions. We want to figure out those solutions. So we're going to go menu, analyze graph, and we want to know the intersection. Now, on your graphs, you have to tell the calculator where that area is because it's not super clever for this. So we need to go on the left, this is the lower bound, and on the right, the upper bound. And there we go. It gives us 0.524. 0.524. So we have 1x, 0.524 in radians. We can say rad. And then the other one, we have to do it as well manually. We need to analyze graph, intersection again, and tell it. Okay, a little bit on the left, doesn't really matter. A little bit on the right. Okay, 2.62. 2.62 rad. All right, and there we've solved that for the domain of between 0 and 2 pi. We have these 2 solutions, and those would be our marks. I just saw someone commented, you're in degrees. Thank you for, I should have looked at that earlier. This is what happens when you're live, you're not thinking straight. So that is how we do it when we're using a graphical way. But yeah, let's look at how we're doing it algebraically. So this is my method. If you have something a little bit different, feel free to use it. So first we're going to get the principal value, either using our GDC. So like I said, remember when we do like x equals sine minus 1 of so and so, I don't know, that's 10 over, just making up random things. When we do that, it's returning one value, or if we use our special angles, our special triangles, we're going to get what we call the principal value. This is our starting point for everything. We need that first. Then we check if it's negative, positive, and where it would be. Depending on the domain, we might need to add or subtract 2 pi for cos or sine, or add or subtract pi for tan, just to be able to make sure we're in, if we're maybe between like minus pi and 3 pi. We'll see a question like this later. Then we just need to find, okay, what's going on, because we know we're getting this. This is the easy part. But what about if we need to go a little bit more that way or a little bit more that way? We just need to add or subtract to figure out what's going on there. And then we might get some extra solutions when we subtract 2 pi or add 2 pi and just check that they're within the given domain that we had. So let's see what that looks like. All right, so a question like this, solve 2 sine x equals 1. They love to do this. They are not just going to give us sine x equals something. We're going to have to move something around, simplify it a little bit to be able to solve for it. Okay, and we highlight our domain. So it's between 0 and 2 pi. Now this is really nice because that's what we're used to working with. So it's unlikely that it's just going to make our lives a lot easier. So to get in terms of sine x, we're going to divide by 2 on both sides. So we get sine x equals a half. All right, and now we can find our principal value. Let's do that. So we want to apply x equals sine minus 1 over half on our GDC, or we can do it ourselves. So when does sine x equal a half? So we want to look at our special triangles. So let's draw them. Oops, sorry, that's a bit in the middle of nowhere. Well, we don't need this one for now. So we can see we're going to get 1 and 2 over there. But that would be for tan. So let's see. We want for sine is a half. There we go. So it's going to be for this one over here. 1 over 2, that means the sine of 30, because that's opposite over hypotenuse. All right, so, and we're in radians, so it needs to be for sine of 30, for 30, which is going to be pi over 6. Just remember, our 30 degrees was equal to pi over 6. All right, so this is our principal value. This is our starting point. Okay, now we check cos. Let's see. We have here, we want to see where is it positive, because here our answer is positive. So sine is positive over here and over here. So we're going to have this angle over here, that's pi over 6. And we're going to have this angle over here, also pi over 6. For this one, we have that one already. That's our first solution. That's our x1. Now for this one, we need to find where this has gone. So this is pi over here, 0, pi over 2 up here. So to find out this part over here, we're going to go from here and we're going to do pi minus this to figure out what that angle is. So for our x2, let me just take out that so there's more space. We need to do pi minus pi over 6. So let's give that a denominator as well of 6. So we can say that is 6 pi over 6. So they have the same denominator, and that just cancels out to be pi. So nothing really has changed there. So 6 pi minus pi gives us 5 pi. 5 pi over 6. And there we go. And we're between 0 and 2 pi, and we know it's only, because this is all the way from 0 on the unit circle back to 2 pi, so it's just these two solutions. So we have that is 1, and that is 2. There we go. Check they're within the domain. Yes, they are. We're good. Okay. Let's try another one. Similar kind of thing, but here can you see our domain is different. So we're going to need to do some adding and subtracting of 2 pi's to figure out a bit more outside of this domain. So we can think of this as we're going to have our usual domain between 0 and 2 pi. That's what we're usually calculating. And then we're also going to have between minus pi and 0. Okay, I'm overlapping some domains here, but it doesn't matter very much. And between 2 pi, let's sneeze, and 3 pi. So these are the extra ones. So we're going to have to minus 2 pi to figure out which ones could be in here. And we're going to have to add 2 pi to figure out which ones could be in here. So we'll come to that in a little bit. So let's start. Again, we need to find our principal value. So there's a 2 in front there. We're going to need to subtract cos x equals minus a half. All right, and x equals, so here we see it's negative, but let's not worry about that for now. Let's just find where, let me actually write it for now, so I don't confuse you. Principal value. We just want to know where cos is a half. So let's go and have a look on our triangle again. All right, took out my triangle. Need to have these copy and pasted. All right, so where is it equal to a half? Well, for cos, we need the adjacent side. So that's going to be 60. Because if we're looking at 60, that's the opposite side. So that's adjacent and hypotenuse. So for cos of 60, and again, we're in radians, so that's pi over 3. So x is pi over 3. This is our principal value. All right, and then we go to our cos diagram. And where is cos negative? Well, cos is positive here and cos is positive here. So cos is negative in this one and in this one. And we're at pi there. So what we're gonna want is that one and that one. So to get this one, we're gonna need to do pi minus pi over 3. So let's do that for, just cut that off. Pi minus pi over 3, our principal value. So we're finding this one. And that is, just for lack of space, put them all with a denominator of 3. So that's 3 pi over 3. Which gives us 3 pi minus pi is 2 pi over 3. All right, so there we have one. We'll check later whether it's in our domain. Maybe I'll just highlight the ones that we have for now. This one wasn't valid. And now this one. So we have pi now plus pi over 3. And again, denominator. So we have 4 pi over 3. All right, there's another one. Okay, so now of these two values, we're going to need to add pi and subtract pi from both of them. So this takes quite a bit of going through. So maybe if I do that here, then it's included. I don't want to erase anything. Feel free to do this yourself as well, because this is mostly just algebraic and good practice. Okay, so let's say my x 2 pi over 3. Now we're going to do plus 2 pi. So we want to figure out on this part of our domain. So we have 4 pi, so that's 6 pi. Oh no, we're over 3. Let's write it all out. Domain of over 3, so that will be 6 pi over 3, which equals 2 pi. So we have 8 pi over 3. All right, so let's keep that one in mind. We'll check it out later if it's in our domain. And then the other one, let's do x equals 2 pi over 3 minus 2 pi. This is a little bit laborious, but we're getting there. Okay, so then we have minus 4 pi over 3. There's another one. And lastly, this value over here, 4 pi over 3, we're going to add 2 pi and subtract 2 pi. So let's do plus 2 pi. Was there anything in the chat? No. 4 pi over 3 plus 6 pi over 3 is going to give us 10 pi over 3. You hope in your exam they're maybe not going to give you such a big domain to check. You're really lucky if they give you between 0 and 2 pi. That's nice because then you're basically just done. All right, and then 4 pi over 3 minus 2 pi. Almost there. Minus 6 pi over 3. So that's minus 2 pi over 3. All right, that is a lot of possible solutions there. That could be in our domain. So let's check, are they in our domain? And just to remind you of our domain, we want, write it in green, between minus pi and 3 pi. Now, all of my things here are currently all over 3. So I'm going to put these as well over 3 because sometimes that also just makes it a bit easier to compare where they are on this. So let's make that minus 3 pi over 3. See if we just cancel 3, that's minus pi. So then we can just compare them. And we want it. So what was I doing? Yeah, so 9 pi over 3. And there, if we just cancel, we get 3 pi. Okay, so let's see first. 2 pi over 3. That's somewhere in there. So yes, this one is good. Then 8 pi over 3. Yep, that's there just under 9 pi over 3. So that's good. Minus 4 pi over 3. That is over here, minus 4 pi over 3. That's outside our domain, so that's no good. 4 pi over 3, still good. That's within. 10 pi over 3, that's over here. That's outside, so that is no good. And minus 2 pi over 3, that's somewhere over here, just in front. So that is all good. So there we have 4 solutions, here, 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 and here. And as your final answer, you can write this as x equals 2 pi over 3, 4 pi over 3. You don't have to do them in order. It's neat to do that, but you don't have to. Nobody got time for that in your exams. All right, I'm all right. What a mission. So there we have our 4 solutions. All good. Let's put it in a nice fancy box. There we go. Final answer. You have found your 4 solutions within your domain. So a lot going on there. I hope I didn't lose you. Let me know if that makes sense or not. If you'd like me to explain it again, maybe in a separate video or something, just again, like I said, you can message me and I'll be happy to do that. That is what we're essentially doing. All right, so time-wise, I think I'm going to skip this one because it is very much the same thing of what we have done here. I would just like to remind you that if you're doing tan, remember here we subtracted 2 pi and added 2 pi because cos and sine are repeating in 2 pi cycles. But for tan, it's repeating in or shifting in pi. So you're only going to, for this, add pi or subtract pi instead of adding 2 pi and subtracting 2 pi. That's the only difference for tan. It's just good to remember that. That everything else follows exactly the same, but when you're adding 2 pi or subtracting 2 pi onto your answers, you're going to be just doing pi. All right, so that is the method that I find works every time. There's not too much like memorizing formulas. You just need to have your cast diagram, your special angles, and adjust for the domain. So hopefully that works for you. All right, then we had trigonometric equations. So just to draw your attention to our identities. The equations are often quite heavily involved with the identity. So this is in the AASL formula booklet. The HL has this as well, and HL also has these ones. Because we're mostly doing HL level, I'm not going to be working with these. However, the process is the same. There's nothing really different that you need to do. It's just you're working with these like they're formulas. So that still applies for you. For AIHL, your formulas are only these two that you're working with. You only use these. And you have a couple of other ones. But again, like I said, it's the same sort of methods. One thing to draw your attention to is, where is it? This one here. The Pythagorean identity, it often is used like this. So you don't really ever see it used like this. Maybe, I mean, not very often, but it's most likely you're going to have to make a substitution like that. So it's just good to kind of have that in mind and recognize what it looks like. When you have it, just go and write it out yourself, like subtract, let's say sine squared theta. And then just subtract cos squared theta from the other side. So 1 minus cos squared theta. Just write these in. It just also helps you save some time. Okay. Then we have a couple of others. So it's good to be quite familiar with these, not to memorize, but just to recognize, like if I have a double angle there, 2 theta, that's the one I could use. Or if I have cos 2 theta, then I have all of these 3. Another thing that they can kind of get hidden there, there's 3 in here you could use, depending on if you want something in terms of cos or something in terms of sine or both. Just remember that there's all of those 3 going on there. So we're going to be using these in solving our equations. All right, little example. So here you need to find sine 2x. Note that they're not saying find x. They're asking you to find sine 2x. So that is hopefully immediately alerting you to one of our identities here. Which one has sine 2x? Well, it's this one over here. Okay, so we're probably going to need that at some point. So if cos x equals 3 over 4, and we're needing to find sine x, let's draw a little triangle. What does that look like? Well, cos is, ugly triangle, adjacent over hypotenuse. So let's say that we have x there. Then adjacent will be 3, hypotenuse 4. And so for cos, we need, for sine, we need opposite over hypotenuse. So the opposite side, we need this one. So we need to find that. We can use Pythagoras because we have 2 sides, right angle, missing a side. I've done that already just to save time, and that's root 7. So to write sine x, remember we're not done yet because we need sine 2x, but sine x is then going to be opposite. So root 7. Oop, why did I write 3? Root 7 over hypotenuse, which is 4. Okay, so we've got sine x, and we were given cos x is 3 over 4. So using our identity for sine 2x, so there's no way to get rid of this 2. We can't divide by 2. We can't move it around. The only thing we can use as our identity is 2 sine x cos x. So it's theta, but we're using x. So 2 sine x cos x. Well, sine x, I know, I've got that. Cos x, I know, I've got that. So I just substitute it. 2 times sine x, which is √7/4, times cos x, which is 3/4. This is also quite a surprisingly common question where they're not actually asking you to find x, just to write something in terms of it. All right, so what is that? 6√7/16. We can simplify further, but I'm not going to bother with that for now. All right, so there is an example. Just going a bit faster because I do want to get to those exam questions. All right. Another common one we see coming up, 2 sine squared x. We have a -3 cos x, but when you're trying to figure out which of these to do, which to substitute, which to change, if you just have a cos x or a sine x on its own, there's not much you can change about that. So it's most often going to involve the thing that has like a squared or a 2x or something like that. So sine squared x, I want to get in terms of cos because I already have cos here in my equation. So if I look for sine squared x, where's sine squared x? Here, there I have a sine squared x. Also here I have a sine squared x. So let's see, I'm going to take this one because I'm thinking that we're going to get towards, well, no, both should work. Yeah, let's use that one. So if I take sine squared x is equal to 1 minus cos squared x. So I've just rearranged this one. I can substitute in for sine squared x. So I'm going to get 2 instead of sine squared x. I'm taking 1 minus cos squared x minus 3 cos x equals 0. That equals 0 is a little hint that we're probably going to have to do some kind of quadratic because we have a squared, we have equals 0. This is going to look like quadratic. So let's multiply out 2 minus 2 cos squared x minus 3 cos x. There we go. I have a quadratic in a trigonometric quadratic. I have my 3 terms. Let me just rearrange. I'm going to move everything over to the other side just to make my leading term, the cos squared x, positive because I prefer that. So 2 cos squared x, change all the signs, plus 3 cos x, and that will become a minus 2 equals 0. So now that is looking like a quadratic, like ax squared plus bx plus c, except instead of x here, I have a whole cos x. So I'm not going to substitute for x. I'm going to call that u. I'm going to say let u equal cos x. I can use any variable, but I've already got x, so I can't do that. And I'm going to substitute out. So I'm going to take out this cos x, and instead I'm going to put in u. So that would be 2u squared, because that's cos x squared, plus 3, instead of cos x, u, minus 2 equals 0. All right, so now I have a quadratic that I need to solve. Let me solve that. Hopefully I can factorize it. Let's see. Well, I have 2, so I only have 2 factors there of 2 and 1. So I'm going to need times, let's say, 2, because that's going to give me a 4u, and then minus 1, so I'll take away and get 3. There we go. Okay, so factorized, let's solve that. 2u minus 1 equals 0, and u plus 2 equals 0. Move that over to the other side, so we have u equals a half, and u equals minus 2. But we weren't working with u, we were working with cos, remember? So I'm going to put the cos back in now. Cos x equals a half, and cos x equals minus 2. Now, alarm bells ringing because cos is only between minus 1 and 1. So this is not possible. It never is going to equal minus 2. Our cos graph only goes between 1 and minus 1. So that's not possible. This one, however, is like one of the ones that we had earlier. In fact, I think we already had cos x equals a half, or did we have cos x equals minus a half? So then what we would do is we would find our principal angle, and I'm not going to do that part again because I did it a few times, so hopefully it's sticking now. But find your principal value of x and then solve for your domain. The domain was between 0 and 2 pi, which I should follow my own advice and highlight, which is nice because then you won't have to reject solutions or add solutions. So I'm going to leave that one for now. I'll finish it afterwards and upload it. If anyone wants these notes afterwards, just reach out and I will email them to you. But for now, I'm not going to do it just because of time. All right, this one would be very similar, where you have a cos 2x. So you need to look at the formulas. Obviously, cos x, there's nothing much that you can do there to change cos x. So it's going to be the cos 2x. And we have a look here. What do we have? Really helps to think of these as just formulas that you're using to help you. That's the cos 2 theta. And we're working in terms of cos, because we have a cos there. So we want something that's going to result in a cos. So we don't want that one because that's going to give us a sine squared. We don't want that. This one's going to give us sine. We don't want sine. So we are going to want to use that one. So we'll substitute 2 cos squared theta minus 1 for that. 2 cos squared x minus 1. Put it in brackets in case there's any negatives for that. Plus cos x equals 0. Multiply out, you're going to get 2 cos squared x. Well, no multiplying out. And then just rearrange them because this is going to be another quadratic. So there you see. This is very common that you end up having a quadratic, just like this last one we did. All right, and then you would solve it in the same way. Again, I'll finish out the solution in the notes if anyone wants that. Okay, so let's do an exam style question. We're bringing in some log revision here. Just checking there's no comments in the chat. No. Okay. All right, so logs and identities going on here. Show that. A show that question is a very important command term that we need to know how to use. So if anything says show that, you can't assume that it's true. So I can't assume that this equals this. So I'm not able to move things around. I can't move things across the equal sign if it says show that, because then I'm assuming it's true, but they haven't said that it's true. I also can't use both sides. I have to pick one side and turn it into the other one. So I can either pick this one and make it look like that, or pick this one and make it look like that one. But I cannot use them both in a show that question. So I'm going to pick one side, and sometimes you might pick a side that maybe results in a bit more work. They all should be able to, in some way, be able to change them over. If you're going somewhere and you're finding that it's not looking like, stop, leave it. If you've run out of time, don't scratch it out yet. But if you have a chance to try the other side, that might work better. So I'm going to go with this side. All right, so log 9 cos 2x plus 2. I have to turn into looking like this. Now, the thing that I noticed with logs, we want them to have bases that are the same. Now, this and this base, they're not the same, so I can't perform any of my log laws. So I'm going to need to try and get that to have the same base. And how I can do this is with a change of base formula. So I don't know if my video is covering it. No, it's fine. So this formula is the change of base formula. It's in your formula booklet, and you can use that. It's basically just, you don't have to remember much. If you have a base A, so in this case, we have a base 9, and A is that value over there. It's just like substituting. This is our X, that whole thing. That's our X. It's going to go there. And b is what we want to change the base to. So I'm going to highlight that. I want to change the base to 3. That's where my change is coming in. So I'm just going to take these different green and red, basically, to change it into a base of 3. So let's see how that looks. So that means I'm going to have log, I want base of 3. That's what I'm changing to, of x. Well, x is just this part here underlined in red, cos 2x plus 2. And log base 3 again. See, we're getting it towards there. Of a, and a was my 9. Don't know how well you remember your log, but log base 3 of 9 is equal to 2. You can think about having like a little block over here. 3 to the power of what gives me 9? Well, it's 2, so this whole thing is 2. So let me replace that there. We have log 3 cos 2x plus 2 over 2. So we've just figured out that that was 2, which is equal to half. If we bring that out in front, log 3 cos 2x plus 2. That half, as part of our log laws, we can put as an exponent over here. So that half is kind of alerting us to the square root. Square root is something like to a half. Okay, we can see where this is going. Cos 2x plus 2 to the power of a half. Well, there we go. That's just a root. And you could even leave it like a half because that's the same thing. But if you want to just make sure there's no shadow of a doubt that you know, plus 2, no, I wanted to do my root now. No, it doesn't want to erase. So let's just put our root in there. All right, so we have shown that this side is equal to that side. There we go. There we have it. So that's a bit of log laws coming in useful there. Now, the actual part of the sign identities. Hence or otherwise, solve this equation. Now, this is a paper 1. So we need to do this without a calculator. And we're between 0 and pi over 2. So let's highlight that. And remember that at the end. I think my computer is having a tough time with all the programs. Let's try that. There we go. We've lost a few things here. There we go. All right, so where am I going to do this? Because I don't want to erase that. If you want the notes, let's do a little screenshot. Whoop. Yeah, sorry, it's really struggling. Okay, that's fine. We'll go here. Okay, so they're saying now, hence or otherwise, this is your clue that you need to use what you used in this previous question. So what we used was that log 9 cos 2x plus 2 is equal to this. Now they're saying solve log 3 of 2 sine x is equal to that. But we're going to take the fact that we know, let's use green, we know that this is equal to this because we have just proved that it's equal. So instead of using this to solve it, I'm going to use this one to solve it because this has a base of 3 and this has a base of 3. So I'm just going to cut out the middleman there and go and solve those two because they have the same base, and that's going to save me some effort. So I'm actually solving the equation log base 3 of 2 sine x is equal to log base 3 of root cos 2x plus 2. All right, and there we have all with the same base. Now, if we have the same base on both sides here, log 3, we can just cancel them. So we can say, we can just drop the logs. So 2 sine x equals cos 2x plus 2, and not forget that root. All right, and now we have just a trigonometric equation to solve. We're still in paper 1, so no calculator for us, unfortunately. Let's try and solve. I see a square root. I don't like a square root, so I'm going to square the other side. So I'm going to get 4 sine squared x if I get rid of that root, which gives me cos 2x plus 2. And now cos 2x, that's also something that is we're gonna need to change. So we go to our formulas here. Let's see, cos 2x, there we go. We need to use this, one of these. Well, I already have, let's see, what do I already have? I already have sine squared x. So maybe I just want to stick to that and do another sine squared x to make this simpler. So let's take 1 minus 2 sine squared x. 1 minus 2 sine squared x. I'm replacing in that 2x plus 2. 4 sine squared x. Okay. Now we have just sine squared x's. Now what can I do? I can put 1 and 2 together. That's actually a saying. 1 and 2 is 3. And I'm going to move this minus sine squared x over to this side. So I'll have 4 sine squared x minus 2 sine squared x, which is going to leave me with 2 sine squared x. All right. Did I... Just checking that all is good. No, sorry. It's a minus. Anyone catch that? Sorry, so minus 2 sine squared x, I'm going to add on the other side. So it's going to give me 6 sine squared x. And I can divide by 6 on this side. So sine squared x is equal to 3 over 6, which is the same as a half. And to get my sine x on its own, I just need to square root both sides. So square rooting both sides. It's going to leave me with sine x equals plus minus 1 over root 2. So that would be a root 1, but that's just 1. And root 2 we can't simplify. So now we have it finally. From this long process, we've got it all the way from looking like that to being in a sine x, which is what we always want to get. We always want to be able to get to our principal value and just have a sine x equals or cos x equals or tan x equals. A little hint that if you get to the end here and this is not one of your special angles or special values, then just double check that something hasn't gone wrong, because in a paper 1 calculator, it's always going to be one of those because you don't have a calculator. So if you're not getting something that looks familiar from the special triangles or special values, just double check you're working, that anything hasn't gone wrong. All right, and now we can apply. So when sine x equals positive or negative, but remember we have this little domain here, restriction, that it's between 0 and pi over 2. So it's just going to be the positive one. Sine goes between, let's draw out the whole thing. Between 0 and pi over 2 is just the first quadrant. It's just this one over here. So we want when it's equal to 1 over root 2. Sine x equals 1 over root 2. And which value is this? This is using our other triangle. 1 over root 2. So when sine is equal to 1 over root 2, that is going to be opposite. Well, it's going to be the same, so it doesn't really matter which angle we use, but either way, it's sine of 45, but we were in radians, so that is x equals pi over 4. That was our 45 degrees. And there we go. That is our solution. All right, so that was quite a big question, but it was 5 marks, so that's really good that we had a lot of marks there. So let's just take a look at the mark scheme. All right, so you get a mark for attempting to use the change of base rule. That was a method mark. Another mark for beginning to solve. Another mark for beginning to solve. An important note that when you have a show that question, you never get a mark for showing the result, but you need to do that anyway. It's like they want to see that you have realized that you've gotten to it. So don't just leave it here and say, done, I've shown that. You need to really take it to the end. And when they have a show that question, it's important to do as many steps as possible to show that you're getting there, because they've given the answer basically. So you need to prove that you really know exactly every step. If you cut too many corners in these in-between steps, they're not going to like that, because you could be just molding this answer somewhere there. There's some very creative looking things that you can, as examiners, you can quite often tell that they've skipped a few of the between steps, but they're not sure how they've gotten there. So try and show everything to show that you really understand. All right, for B, we had, yeah, nothing too crazy here, just solving questions. It's important to note about the domain. If you showed other solutions because you didn't know the domain, then you would get a 0 for that. So you wouldn't get that final mark. So if you said, even though you have pi over 4 and you said, I don't know, 5 pi over 4 like that, they wouldn't say, okay, well, you've got that one, so that's 1 mark. They would give no marks because you said that's the solution, but that's not the solution. That is. So that's really important for the domain, just to look back on it. Right, running out of time, but we have another type of show that question. Again, these are very common type of thing. Again, you're going to use this. Remember, it's one side. You've got to show equals another side. So you cannot use this if you're using this. And you might be tempted to move things across. You can't. You can only pick one side and move the other. So let's quickly look at that one, because I think it's a quick one. Only 2 marks. So there's not much you're going to have to do here. And I'm just going to show you how you are encouraged to write it. So I'm working on this. I'm going to say equals left-hand side, LHS. This is a nice way examiners like to see this. So you're not saying it equals that yet, but we want to say equals something. So we're going to say equals left-hand side to show that I'm building on this. I'm working on this side. Then that cos 2x we want to change, so it's going to be cos 2 theta over there, and we have sine x here, so that means we're going to want the one with sine, not that one because that's just cos, not that one because that's cos and sine. So this one, 1 minus 2, so it's open brackets 3, and instead of cos 2x I'm writing 1 minus 2 sine squared theta plus 11 sine x equals left-hand side. I'm not saying it's equal yet. Multiply out, so we get 3 minus 6 sine squared theta. Sorry, x plus 11 sine x. And can you see, we've got it already there. 3, positive 3, negative 6 sine squared theta, and positive 11 sine x. There we go. So you can say left-hand side equals right-hand side. That is our proof that we know it's equal. Then, hence, or otherwise solve this equation. So solving this equation between 0 and 180 is then going to, you can already use this that you have changed it into, because you've got this, that was, where are we now? You've already got that side, so you can use that to solve. All right, and I have the answers. I have a whole bunch of these kind of questions that if you want to go over them, I think what I'm going to do is actually make a folder with all of the topic notes from all of the sessions and then include in all of them past paper questions on those things. And we also have the homework topic. So if you want more exam style questions with the mark schemes, just let me know on Miss Ivy Maths on Instagram. Just private message me, DM me with your email address, and I will share the folder with you. I think that's probably going to be the easiest. So funny that this is my exact point here, and then I went and did it and didn't check. I was working on my calculator before, and it was in radians, or so I thought. But make sure your calculator is in radians. Write in big letters at the top of the question when reading it. So each time we saw these questions, let's see the exam question, like this one, we highlight it to remember to check the domain, and I would write it like this. I would say like degrees in like another color at the top, really big. The examiner is not going to mark you down for that as long as you're not covering your working and you're not in the box writing space. Like really big, so you know to make sure your calculator is in degrees, because you're going to be switching all the time from degrees to radians depending on the question. And also to make sure that you're giving your answer in the right way, never mind just using your calculator. Verify your solutions using a calculator if you have it. Check them graphically if you have your calculator. Just saves so much time. I'm still laughing at this. You'd be surprised how easy it is to forget. I forget. And then don't forget to too much talking. Memorize exact values and special angles, because that is very important for paper 1. For paper 2, you don't need to. It's one less thing to think about. Now, there's a whole bunch of notes on the Exam Dojo platform on Learn for each topic. They're really good with everything and lots of worked examples. And there will be a homework assignment with more questions if you want. Class codes are on the info page. Wow, that was a lot. Quite an intense topic. There's just so much going on and so many different things. It's quite hard to condense into 1 hour, but I hope it made sense. I feel like I might have lost some people on the many solutions to that one equation where you have to add 2 pi minus 2 pi all the time. That was probably not the most fun thing you've ever watched on a Saturday. But yeah, let me know if it made sense, the method that I use, or if you have a different method, then yeah, go for that. But hopefully that helped and you're feeling clear about how to answer these things. All the questions are in trigonometry going to come down to these identities that you just use as formula. So yes, any questions? Anything at all? Or any topics that you want me to do next? I have a list on the link that I shared on the info page with all the upcoming sessions. We put a lot more on now, but we have a few more sessions that we're still going to add. So if there's any topics you want to see, please put them in the chat. Just give it a moment because I think what's being shown is a little bit delayed, so it might take some time. Or maybe you're all just really done for this Saturday. Okay, I am going to assume there are no questions. And thank you for joining. I hope that it has helped in some way. But yeah, have a lovely rest of your evening and perhaps see you tomorrow or in the week for the next sessions. Goodbye.